Hi, welcome to your video on exponential growth and decay. You will be able to write and solve exponential growth and decay problems, so let's get started. Exponential growth is the first thing we're going to talk about. Things are growing in these types of equations, and you will see graphs that look like this. As you're moving left to right, they're increasing. If you think about the algebra behind it, A is greater than 0 and B is greater than 1. And then the base B is called your growth factor, which equals 1 plus the percent rate as a decimal. And we will talk more about that later. Basically, here's the algebra behind it. A is your initial amount that you have, so when x is 0. And then you have B, the base, which is greater than 1. That is the growth factor. And then you have x, which is just the exponent. I'll give you an example of an exponential growth type of problem that you will see. Here is the problem in economics. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, it was $360 billion was spent. If the trends continue, how much will be spent in restaurants in 2015? So we're going to use that equation, and we'll actually put it up here so you can see it a little bit better. We're going to use that equation. So when A is your initial amount, that's how much at time 0, and that was $360. Or sorry, $360 billion. And then you're multiplying it by B. B is your growth factor, and I mentioned previously that B is talking about 1 plus the percent rate. And so what that means is it's always going to be 1 because it has to be greater than 1. And then your percent rate is 7%, so it's 1.07. So you're factoring in that percent in that way. And then your x is your exponent. That's how much time is passing by. In this case, we're going from 2005 to 2015, so that is a time span of 10 years. So you're substituting in 10 for x. And then you just evaluate this order of operations. So you do 1.07 times to the 10th power, and then you take that and you multiply it by 360. Obviously, you can use a calculator for that, and you will end up with an answer of about 708, and so that would be $708 billion that we're talking about. All right, it is your turn. Here's the example problem. The population of Maple Grove was 25,000 people in 2000. If the population grows at 1.5% each year, what will the population be in 2025? Please enter this information on the Google form. Compound interest is a type of exponential growth that we're going to talk about really quick. Here we have what the formula is. It is A equals P and then parenthesis 1 plus R divided by N in parenthesis times N to the T, or T times N power. And as you can see what each thing is labeled as, I do want to point out that the number of times interest is compounded per year. If it tells you it's compounded quarterly, that's 4 times, semi-annually is twice, and so you just got to pay attention to that. It is an important detail when you are factoring in these types of questions. And I will give you an example right now. In finance, suppose when your friend was born, your friend's parents deposited $2,000 into an account, paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So you're basically going to use the formula and insert in everything you know. So here I know, for starters, I know I don't know the balance because that's what I'm trying to find out, but I do know what the principal was. In other words, the initial deposit, and that was $2,000. So right now I'm just dragging and dropping what I know. The 1 will never ever change. It'll always be 1 plus. And then R is my annual interest rate, which is 4.5%. Because it's percent, we have to write it as a decimal. So 0.045 over N. N is the number of times it is compounded each year. It's compounded quarterly, which means it's 4 times a year. And then times N, which is 4, times T, which is the number of years, and that is 18 years. As you're solving this, you will then do your next point of multiplying the exponents together. So nothing else changes. Except for the exponent. And then now that we have this, we can evaluate it a little bit better. If you wanted to do it more at one time, so I guess you could have combined 2 steps together. You could have calculated what 1 plus 45 thousandths divided by 4 was, which you can use a calculator to do, and that would give you 1.01125. And obviously I'm using a calculator for that. So now that I know what my base is for my exponent, I can evaluate exponents first and then multiply by 2,000. And when I do that, I'm going to get about an answer of 4,475.53. And you can go ahead and check your calculations to make sure I'm doing this right. I make mistakes too sometimes. But the account should have $4,475.53 in the account after 18 years. Exponential decay is another type that you will see. Very similar, except for now it is decreasing. And the picture of a decreasing model would look something like this. So exponential decay. And as you can see in this example, B is greater than 0, but it is less than 1. And that's the distinguishing factor because B is what's called the decay factor. So you have 1 minus the percent rate of the change expressed as a decimal, and we'll talk about that some more in our example. The algebra behind it is here. Y equals A is your initial amount when X is 0. So in other words, typically your time is 0. B, the base, is between 0 and 1. That's the decay. And then, of course, you have your exponent. So if you use that, it is helpful for your problems. Here we have physics. A kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101. For every 1,000 meter increase in altitude, the pressure decreases 11.5%. So what is the approximate pressure at 3,000 meters? So we're going to use the formula and just fill in what we know. The first thing I know is that Y equals, and that initial rate, or the initial amount, my starting amount is 101. Because that's at sea level. That's 0, my starting point is 101, so times, and then B is my decay factor, and it's decreasing at 11.5%, and so that is going to be what I subtract from 1, and so I'm going to write this as a percent, so it's 1 minus 0.115, and that gives me 0.885. So that's actually what my B is. So when I was just explaining subtracting 1 from it, this is what I'm talking about. So you're giving your percent and then you subtract 1, and then that is what B is. So don't forget that step because that's really important, because otherwise it's not going to be a decay factor anymore. And then we have to our power, which is our time. So there's our equation. Now it's at an altitude of 3,000 meters. So that's what I'm going to use. So 101 times 0.885. Now we're talking about going from 1,000 meters to 3,000 meter increments. That's really important. Every 1,000 meter increase. And so how many times does that increase? It just increases 3 times. So here's now how I'm going to evaluate it. Exponents first and then multiply by 101. And you should get y to be approximately 70. So my answer then is that the pressure of the altitude at 3,000 meters is about 70 kilopascals. Your turn. Population in Maple Grove is 55,000. They decide Rogers is a much better place to live, so the population decreases 2% each year. What will the population be after 15 years? This you will also put in a Google Doc, so check my website to find the link. This is the end of your video. Just another reminder to enter those your turn problems onto Google Forms. Thanks for watching. Have a great day.